In our previous video, we had hypothetical pre-test, post-test data that we erroneously analyzed using a two independent sample t-test, ignoring the fact that the two samples were not independent of each other. It's actually the same people being measured before and then after they received an intervention, right? And specifically in that example, we were looking at whether an intervention could have had an impact on student math anxiety levels. Unfortunately, we saw that the results were a little disappointing and we were not able to reject the null hypothesis. We couldn't conclude that the intervention changed anxiety levels. Bummer. But again, while you can analyze pre-test, post-test data, or any data where there's that one-to-one connection between individuals in each sample, you can analyze that using an independent sample t-test. There's actually a much better way. So now, let's do it correctly, okay? Now, recall that kind of where we left off, we had 6 students with math anxiety who took an anxiety survey as a pretest. Then they participated in intervention and took a survey again as a post-test. So here are the results. The mean anxiety level was 7 at the pretest and it declined to 5 at the post-test. But given the variability we saw in the data and the small sample size, the drop wasn't large enough for us to reject the null hypothesis. We just couldn't conclude that there was in fact a real change in anxiety levels following the intervention out in the population of all students with math anxiety who could get the intervention. The chance of seeing this 2-point difference, that drop of 2 points, was just too great that it was just random noise, random sampling error, okay? Now, while we're here, before moving on, let's note that the pooled standard deviation for the pre-test and post-test scores was 2.145. We calculated that in the last video, and that's going to be important in a minute, so keep that in mind. We'll come back to it later, all right? So now let's analyze this exact same data correctly using a paired sample t-test, right? So how do we do that? Well, first we calculate the difference between the pre and post-test score for each student. So that would be, for the first student, that would be 4 minus 2, right? Second student, it'd be 6 minus 5, 7 minus 3, etc., etc. We go on and do that for all 6 of the students. Right? So we get 2, 1, 4, 0, 2, 3 as our difference scores. Now, notice that there's 6 difference scores. This is important because we're going to focus on the difference scores. Our sample size of difference scores is 6. Now, for clarity, we're going to label it as n sub d to emphasize that it's the n, it's the number of difference scores that's equal to 6, and that's what we're going to be focusing on now. If we add up those difference scores, we get a sum of 12, which divided by our n of 6 gives us a mean difference score of 2, right? Which we'll abbreviate as d bar, just to be clear that it's the mean of the difference scores. So what's the standard deviation of those difference scores? Now, to calculate that, let's kind of clean things up a little bit and slide the difference scores over to make a little room for ourselves here. Okay? To calculate the standard deviation of the difference scores, we subtract the mean from each person's difference score. That gives us the deviations from the mean difference score. So that's 2 minus 2, or 0, 1 minus 2, or minus 1, and so on for all the deviations from the mean difference score. We then square each of those deviation scores, giving us 0 squared is 0, negative 1 squared is 1, 2 squared is 4, and on and on. Those are our squared deviations, our squared deviation scores for the different scores. We then sum up the squares of the deviations of the different scores. That's a lot of D's. The deviations of the different scores, we add those up, and that gives us a sum of 10, which is our sum of squares for the different scores. Okay, see where we're going? So our sum of squares for the different scores is 10. Okay, now the variance is the sum of squares divided by n minus 1, and the standard deviation is the square root of the variance. So that would be the square root of 10, our sum of squares for the different scores, divided by 5, 6 minus 1. Remember, it's our focus, our n now is those 6 different scores. So 10 minus 10 divided by 5 gives us 2, well, right? The square root of 2 is 1.414, and that's our standard deviation, right? So that's the standard deviation of the difference scores. Now, let's go back to the original pre- and post-test scores for a moment. We saw that the pooled standard deviation based on the actual pre- and post-test scores, the pooled standard deviation was 2.145. But the standard deviation of the different scores down there is only 1.414, about 1/3 smaller. Now, that's going to have big implications in a minute when we calculate the standard error and the t-score. But first, you may kind of ask, well, what happened? How did that happen? Why is the standard deviation for the different scores smaller, in this case a lot smaller, than the pooled standard deviation based on the original raw scores? Well, notice that while there's a lot of variability in the pretest scores and a lot of variability in the post-test scores, the pretest and post-test scores vary together. They co-vary. They're correlated with each other because of that one-to-one connection. Students with higher pretest scores tend to have higher post-test scores. And students with lower pretest scores tended to have lower post-test scores. As a result, the different scores remove that part of the variability that's due to some kids having overall higher or overall lower anxiety. The different scores takes out some of that variability that we see kid to kid and their overall anxiety levels. Pretty cool. Okay, so that's kind of interesting, but let's look at the consequences of that, right? Of that smaller standard deviation when we use that in our paired sample t-test. Okay, so a paired sample t-test is essentially a one sample t-test. See, I already know how to do it, but we're using different scores now in that one sample t-test. So the formula for a paired sample t-test is really just the same, and we're just going to tweak the notation slightly to emphasize that we're talking about different scores now. So t is equal to d bar instead of x bar, right, to emphasize it's the mean of the different scores, minus mu naught divided by the standard error of the mean for different scores. So it's s sub d bar instead of s sub x. But it's the same old one sample t-test formula, right? Now, we'll come back to this, particularly mu naught, in a minute, okay? Now, the standard error of the mean for our different scores is just the standard deviation of the different scores divided by the square root of n. Remember, 6 different scores, so n is 6 in this case. Now, we just calculated the standard deviation for our difference scores, and that was 1.414. So if we plug that into our standard error of the mean formula, we get 1.414 divided by the square root of n, right, again, and that's the n of the difference scores. So it's the square root of 6, right, is our formula, the standard error of the mean. That works out to 1.414 divided by 2.449, and if we use non-rounded values, we get 5.77. If we then plug that into our t formula, we get t equals d bar minus mu naught divided by 5.77. Now, we calculated d bar, the average of our difference scores, a little while ago, right? That was equal to 2. But what's mu naught? Remember, mu naught is the value we expect to see if the null hypothesis is true. In this case, our null hypothesis would be that there's no difference between the pre and post-test scores, right? Well, if there's no difference between the pre and post-test scores, then we'd expect the mean difference for those different scores to be 0 if the null is true. So mu naught is just 0, and it drops out of the equation, giving us t equals 2 divided by 0.577, which gives us a t-score of 3.464. And of course, our degrees of freedom for the one sample t-test is n minus 1. But remember, n is the number of difference scores. It's the number of pairs that we have in our sample minus 1. So we add 6 pairs, 6 different scores, so 6 minus 1 is 5. Our degrees of freedom is 5. Right? So based on this, we can write out our statistical notation and kind of write that out as being t with 5 degrees of freedom in parenthesis is equal to 3.464, right? And if we look that up using a calculator, we find that the p-value, two-tailed p-value, is equal to 0.018, which is less than our alpha level. So now we will reject the null hypothesis. The data suggests that there is a difference between the pre and post-test scores. Pretty cool. But remember, a few minutes ago, we failed to reject the null hypothesis with the 2 independent sample test. So what happened? Well, here's a summary of the results for both analyses. When we look at the t-test, notice that the numerator is the same. And if you think about it, that kind of makes sense. In both cases, the numerator is the difference between the pre-test and post-test means. And the difference in means doesn't change based on whether we calculate the pre-test and post-test means and then the difference, or calculate the difference and then the mean of those differences. It's kind of getting to the same point, right? So the numerator is the same. But here's where it gets interesting. Notice that the standard error for the paired t-test is smaller than the standard error for the independent samples t-test. In this case, it's a lot smaller. That's because, as we saw earlier, the standard deviation for the difference scores is reduced relative to the pooled standard deviation based on the raw pre-post scores. That reflects that the difference scores removes part of the variability due to some kids having overall higher scores and other kids just having lower overall scores. Right? We've taken that the different scores has taken some of that variability away from us, which is a good thing. It gives us a smaller standard deviation, and a smaller standard deviation translates to a smaller standard error. All right. Now, that smaller standard error combined with equal numerators gives us a larger t-score for the paired sample t-test. And that's great because all things being equal, we like larger t-scores because the larger the t-score, the less likely the null hypothesis is true, and the more likely we'll be able to reject the null. You may kind of recognize that, well, all things aren't exactly equal. With the paired sample t-test, we did cut our degrees of freedom in half. Ooh. We had 10 degrees of freedom when we did the independent sample t-test, but we only have 5 degrees of freedom with the paired sample t-test. And this creates two kind of somewhat opposing factors: larger t-scores, but smaller degrees of freedom. And if you think back to how the shape of the t-distribution changes based on the degrees of freedom, right, you may start to recognize something here. Here's two t-distributions where the red curve reflects a t-distribution with a large number of degrees of freedom. And that blue distribution reflects a t-distribution with relatively few degrees of freedom. The smaller the degrees of freedom, the thicker those tails will be, right? The more results we expect to see in the tails, even if the null is true. With smaller degrees of freedom, we expect to see bigger t's even if the null is true. So for any given t-score, the p-value gets larger as the degrees of freedom get smaller. Now, in the case of the paired sample t-test, that might make you a little nervous because we're giving up half our degrees of freedom. We're cutting those degrees of freedom in half. They are getting smaller. But don't worry about it because, yes, while the smaller degrees of freedom may tend to make p-values a little larger for that t-score, that reduced standard error and the larger t-scores you get by doing the paired test more than offsets that effect. It's well worth it. I mean, look at the difference in the results. We go from a p of 0.1374 and failing to reject the null to a p of 0.018, right? And rejecting the null when we do the paired sample t-test. In practice, I got to tell you, I can't recall ever having data where the results weren't stronger using a paired test. To the contrary, I've seen numerous situations where this happens big time, where there's no significant findings if you look at them independently as independent samples. But when you then look at them as a paired sample, suddenly the results become significant. I've seen that more than a few times. This is why we like to have paired or matched samples. Now, it can be paired using pre-post scores like we've seen in this example. It could be also paired in other ways, like you match students with similar reading skills and give one an intervention and one gets the standard curriculum. And you do that for a bunch of students that you've matched, again, based on their reading skills before they get the intervention. Or other ways that you can end up with these sorts of matched samples, right? So, okay, so that's the paired or dependent sample t-test. Same thing, just different people call it by different names. And it also, really, the purpose of this is to highlight the power of matching participants. It's a very good thing whenever you can do it. Now, because it's so powerful, you'll see the same idea and the same principle used in other more elaborate statistical tests as well, because everybody likes doing it. So it's definitely worth taking advantage of matching your participants whenever possible. All right? With that, let's wrap up the video. Okay? Take care. Bye-bye.